The Atmega 328 is a popular microcontroller among electronics hobbyists, engineers, and makers alike. The main reason for its popularity is, of course, because it is the core processor of the Arduino Uno. The Arduino C++ language provides quite a few easy-to-use built-in functions and libraries that allow developers to focus less on complicated configuration and more on what they want a program to do. Consider analogWrite, the function for controlling pulse width modulation. Once it is executed, the selected pin will continue to toggle at the desired duty cycle while the rest of the program moves on. Have you ever stopped to think, I wonder how exactly the microcontroller produces the correct PWM signal in the background without any sort of loop? Would you be surprised to find the answer involves triangle waves? In this video, we will explore the inner workings of this versatile AVR and learn what happens under the hood of the analogWrite function. Arduino is an open source project, right? That means we should be able to find all the source code for analogWrite. Every Arduino installation contains the Arduino core, all the code that provides the built-in commands we've come to know and love, including analogWrite. After a bit of hunting, I found the core in the installation folder located in hardware/Arduino/AVR/cores/Arduino. It could be in a different place in older versions, but it's in there. Two of these files are important to us. The implementation of analogWrite is in wiring_analog.c, and some additional PWM setup code is found in the init function of wiring.c. What, you might ask, is wiring? And why wouldn't the Arduino core files use names like Arduino_analog.c? It's time for a brief history lesson. In 2003, a bright Italian fellow named Hernando Barragan created an open source board called Wiring using the Atmega 128 and produced an IDE derived from processing. Take a look at this. It's a SparkFun wiring board, now retired. Later, in 2005, wiring was forked and became a separate project named Arduino. David Mellis ported most of the wiring API to Atmega 8. Today, the Arduino core is a mixture of older wiring code and newer Arduino additions. The names of the files tell the story. Keep this in mind as portions of the code may apply only to older microcontrollers and not the 328. Let's check out the analogWrite function, which begins on line 100. Aha, I see a call to a familiar function, pin mode. This will ensure the pin is configured as an output so it can source and sync large currents. We also see that if the duty cycle is 0, no pulse is produced because the pin is held low. Likewise, the pin is held high when the duty cycle is 100%. So far so good, but now it gets interesting. A helper function determines which timer module the pin argument corresponds with. The rest of the function is one enormous switch case statement that contains nearly 20 identical cases. Only one will run depending on the selected timer. The first case is apparently a fix for the Atmega 8, a predecessor of the Atmega 328, which was used on the original Arduino board. Let's skip to the next case. Only two things are happening here. The COM0A1 bit is set in TCCR0A. The comment informs us that this action will connect PWM to pin on timer 0 channel A. And the argument val is loaded into the OCR0A register, which somehow sets the duty cycle. Yikes, we're going to have to reference the datasheet to figure out what's going on. So open up the datasheet to Chapter 19 to the register descriptions of timer 0 on page 138. Table 19.4 tells us that in fast PWM mode, setting COM0A1 in timer counter 0 controller register A will clear OC0A on compare match and set OC0A at bottom. Well, that's about as clear as mud. Let's switch over to the scratch pad and do some sketching. Here we are at the scratch pad. Before we can talk about how an AVR produces PWM, we have to discuss the timers. And before actually we can fully understand the timers, we need to learn to count in binary. Don't worry, it's easy. First, we're just going to create a table. Oh boy. And it's going to be a table with 10 rows. And 4 columns. Ten rows because we will count from decimal 0 to decimal 9. But we'll do it in binary. Step 1. Alternate between 0 and 1. The first one should be a 0. And we do this on column, the rightmost column. Then we move up to the next column. This time we repeat 0 twice, and then repeat 1 twice, all the way down. So this is 2 times the third column. We repeat 4 times. And the last column we repeat 8 times. See, I told you. Easy. Now, let's look for patterns. First, let's cross off all the leading zeros. Because just like in decimal, the number 051 is just 51. Okay? So we'll cross off the leading zeros. They're just in the way. And you could rewrite this table without them. Now find all of the places where all the digits are 1. So that occurs here, here, and here. At 1, 3, and 7. Notice that on the next number, that 1 switches to a 0, and you have a 1 in the next column. Again, the 1s switch to zeros, and you have a 1 in the next column. Same pattern. It appears to be a carry, the sort of thing that happens when you go from 99 in decimal to 100. In fact, it is a carry, and this carry behavior is critically important. Now, on to timers. The Atmega 328 has 3 timers. Timers 0 and 2 are both 8-bit timers, which means they can count up to 255. Timer 1 is a super timer because it's a 16-bit and it will count up to 65,536, which is 2 to the 16 minus 1. Computers start counting at 0, and that's why we subtract 1. For simplicity, I'm going to be working with timer 0 for our demonstrations, The timer will increment on every clock cycle. Now you can configure timers to count downward or to count slower than the system clock, if you wish. But what happens whenever a timer reaches its limit? In order to find out, we'll extend our table. Obviously, these 4 bits are going to fill up and we're going to need to draw out all 8. So let's say our counter has made it to 255, which occurs when all 8 bits are set, are 1. 256, 256, following our carry pattern, would be 1 in the next column with zeros the whole way across. However, there's no more room for this carry bit, and so it gets ignored. And the result is the value currently stored in the counter is equal to decimal 0. So it has returned or reset back up to the top. And on the next cycle, it will count to 1, and then 2, and then 3, until it reaches 255. It will then reset on the next cycle back to 0. We call this timer overflow. You can configure your AVR to run an interrupt service routine on each timer overflow and create periodic events, that occur exactly once every millisecond or something. This is also how Arduino implements the delay function and the millis function and the micros function using this timer counting. However, that's not how PWM is done. We're going to have to dig a little deeper. Each timer module on the Atmega 328 has 2 output compare units. Okay, so timer 0 has output compare 0, A, and B. Timer 1 has an A and B, timer 2 has an A and B. The purpose of an output compare unit is to, there's a output compare register. Output compare output compare register 0 A is corresponds to, you got it. This register is just an 8-bit number that you can set it between 0 and 255. And when you do, after each timer tick, the CPU will compare the value stored in the output compare register with the current value of the timer. The current value of the timer is stored in TCNT 0 or 1 or 2, depending on the timer. It gets compared with the output compare register. And if they're equal, it will produce a compare match. Now that term sounds familiar from somewhere. Oh yes, it was in the data sheet. We were looking through the implementation of analogWrite, and that led us to a truth table which said that OC0A is cleared on compare match and set at bottom. OC0A is just the name of the pin corresponding to this output compare unit, and that happens to be port D6, which also happens to be digital pin 6 on the Uno. When the compare match happens, it will clear or drive low D6, and when the timer hits the bottom right after an overflow, it will set high D6. It's still kind of hard to visualize what's going on, so let's graph it. This will be count, the current count stored in the register, versus time. We know that the top value is 255. And somewhere between there and 0, we've loaded the output compare register with some value. So starting at 0, after a clock cycle it will count up. My clock cycles are exaggerated, they're really big because I have to get to 255. Fair enough. We hit 255, and on the next clock cycle it overflows back to 0. And it keeps on counting. And it does this again, and again, and it keeps going. You can see we're starting to form this triangle wave. What happens if I shade in the regions where digital pin 6 or output compare 0A is high? Well, we said it's going to set at bottom, so it's going to start out set, it's going to start out high, and then when the counter reaches this line, this threshold of output compare register, it will be cleared low, and it will continue that way until the timer overflows and sets again. Now, something very fascinating is happening here, and if you don't see it yet, go ahead and graph the logic level of D6. We're starting high, and then we drop down low. And then high, and then low, and then high, and then low. Yes, this is pulse width modulation. So who would have thought that a triangle wave would be the structure by which an AVR produces pulse width modulation? Very fascinating. But what's equally fascinating is that there are other fields or areas of electronics that utilize triangle waves. And I want to take a look at an example. There is such a thing as a Class D amplifier. Which modulates an analog input voltage into a varying pulse width digital output. Other classes of amplifiers, A, B, and AB, operate a transistor in the active region. In this state, small changes in current through the base cause enormous changes in current from collector to emitter. It's acting like a variable resistor controlled by the base. But also like a resistor, the limiting current flow is done by dissipating heat. And heat is wasted energy and inefficient. Class D amplifiers, on the other hand, convert the analog signal to digital so that the transistor spends all of its time in the on state, where fully on, where the resistance is nearly zero and no energy is burned, or in the off state, where of course the resistance is infinity and no current flows at all, no energy is burned. And so the efficiency is high. But how do we do this conversion? And it turns out all we have to do is compare the input voltage with a triangle wave generator. And each point where the triangle rises above the input voltage, we shut the output off and we turn it back on again at the beginning of the next triangle wave. This is the exact same process. So we can represent this with a comparator where the non-inverting input is taken from our analog voltage and the inverting input is taken from triangle wave generator. Just like that. So the comparator's job is to play the analog input over top of the triangle wave generator, and each point where the voltage is higher than the analog voltage is higher than the triangle wave, they will turn on and turn off at other points. This is an actual triangle wave produced by voltage, not just a number incrementing inside a computer. But the output result is the same, pulse width modulation. Well, I hope that you have enjoyed this little adventure through AVR datasheets and Arduino source code. Hopefully now you have a better understanding and appreciation of what goes on under the hood of everyday Arduino utilities. I look forward to hearing your comments on this topic. As always, thank you for watching this episode. I'll see you next time.